And for our next presenter today, we have Krzysztof Suwada, who will be presenting Turning Design Mockups into Code with Deep Learning. Krzysztof is a data scientist focused on applying machine learning and mathematical methods to solve business problems focused on developing end-to-end solutions. He is currently focused on neural networks, deep learning, and NLP applications. He is a mathematician, software developer, and trainer. He is also a fan of Albert Einstein's quote, "If you can't explain it simply, you don't understand it well enough." Please help me welcome Krzysztof. Krzysztof, the screen is yours.
Thank you. Thank you very much for the introduction. It's a pleasure to be here today, despite all the circumstances that are around us in Poland. So today I will be talking about, we may call it a POC of turning design mockups into code with deep learning. Just a few words about myself. I work for a startup, Polish startup called Brainly. Maybe some of you have heard about it because we help students to learn, and especially nowadays, I think it's a good option for the kids to check. And I'm also a Google developer expert in machine learning. So this is why I'm here today with you all. So today we'll be talking about two things. We'll begin with the problem formulation. We'll say a few words about image recognition, about processing, language models, and all those things will be just some basic building blocks that will help us create and prepare a solution that at the end of the day should help us generate HTML code. So what is the problem formulation? So basically, on the left-hand side, we have a screenshot, we have maybe some kind of a picture, and on the right-hand side, we have an HTML code. HTML with JavaScript, with CSS, all this kind of stuff. And this is actually more or less how it works in each and every company. So we have a bunch of people that design websites, that are UI designer, UX designers, graphic designers. They create the graphics for us. They create the design of a website, and we have a separate group of people like front-end developers, back-end developers that do the coding. So how about if we could speed up the process of at least the first iteration, like if we could generate HTML code with CSS, with all this stuff, based only on a screenshot, based on a mockup created by a UI designer. So to do so, we first need to somehow extract some of the features, extract information that is present on this screenshot, on this mockup. And we are going to begin with an image itself. You may say that, okay, we already have some kind of representation because we have a numerical representation of the image. This is just simply the RGB, and we have all the pixels, so we know what is on the picture. We have it stored in computer memory. Yep, that's right. But the understanding of those numbers is something completely different than for a computer than for a human being. For a computer, it's only about the intensity of the pixels, which color it is, and how to display it. It doesn't contain any information whatsoever about what actually is on the picture. Is it a cat? Is it a dog? Where is the button? Where is the header? Where is some, I don't know, enumeration? Where is the footer? This kind of stuff. So we don't have this information embedded in those array of pixels. So what we have to do is we need to somehow extract features that can be then used by deep learning network to generate code, because this is our ultimate goal. So we begin with the image, then we will be building features using pretty simple methods like convolution, spooling, basically filters. And we will apply also some final transformation. Sometimes it may be needed, sometimes may not. But basically it will be like pooling, concatenation of features, and maybe adding some additional layers to make it sometimes easier for a neural network to deal with the complexity of the task. So this is our problem formulation on a flow diagram. We have our input data set, which basically consists of two subsets. The first one are the screenshots, or should be some screenshots or mock-up designs. And the second subset, like in parallel, are the HTML codes, the HTML markup of the corresponding design. And this is because we are going to use supervised learning, and we'll teach our neural network to translate image to HTML code. So basically, once we have our data set, and all the things that I will be talking about is based on an excellent blog post and excellent paper about pixel to code. All the links you will find at the end of the presentation. But basically, we have two types of features. We have image and we have language. And by language, in this case, I mean HTML code, but in general, it doesn't really have to be HTML. It can be domain-specific language. I will show you an example at the end of the presentation. But in general, it can be any kind of language. We will extract image features. We are going to extract language features. Then we will feed it to the neural network. And hopefully, our neural network, our deep learning neural network, will be able to generate an HTML code for us once properly trained. Actually, this task can be seen from a completely different angle and can be approached even without saying anything about HTML code generation. Imagine a situation that you have a bunch of photographs in your family album, and you are looking for pictures that with your beloved dog, or I don't know, cat, or whatever pet you like, and you would like to specify the query using natural language, like I want all the pictures with a dog. And to do so, actually, we would have to build something similar in architecture, at least, because we would have to build a solution that would caption the pictures. So describe what is on the picture. And this is not that different, because in that case, we would be using our natural language like Polish, English, or something. And in this case, we are going to do exactly the same thing. We want to describe what is on the picture, but this time we want to be more precise. We want to use HTML. So our first step is to extract image features. And to do so, we'll be using two types of operations. The first one is our convolutions, and the second one are poolings. Those are pretty simple, at least from a mathematical point of view, operations that to be applied on our image, but yet they are able to bring us an amazing value. So a quick refreshment, because I was told that on this conference there were a lot of topics on machine learning, so I will just try to refresh your mind what the convolutions are. So, sorry. On the left-hand side, we have a picture. This is this yellow matrix. On the center of my screen, there is a convolution kernel, which we actually overlay on the image on the left-hand side. And what we do is simply pointwise multiplication, and then we calculate the sum of those numbers. And this is how we got this 5 in this RI, in this red array on the right-hand side of the screen. So basically, this is some weighted sum of pixels. And what we do is we actually, in a loop over the entire image, overlay this kernel, and we get the following representation. And max pooling operation is at least a little bit similar. We also have some square that we overlay on our image, but this time we do not calculate any weights. We don't have any weights. This is much simpler operation. We just take the maximum value in the area. And we, again, put it in a resulting matrix. And as you probably have noticed, the resulting image, both for convolutions and for max pooling, in many cases will be smaller than the original one. This is not always the case. Sometimes we can, there are some special types of padding and moving this kernel or this overlay square over the image, to maintain the original size. But this is something actually up to the machine learning engineer or data scientist to decide how he or she wants to approach this issue. There is nothing wrong with decreasing the size of the image. Okay, and here we have some examples of max pooling. So the first square, the maximum value is 7. Here it is 5. 5 again. Yeah. And we actually loop over our image, and this is the result that we get. And you may ask, why are we going to do all those things? What is the reason? So the reason is to actually extract features. And what a feature is, if you have ever used a software like GIMP or Adobe Photoshop, there is a set of predefined filters that can do many things for you. I think one of the most common or the easiest to spot is on image is like something called edge detection. And the edge detection works exactly the same principle as a convolutional filter with some predefined weights in this filter. And as a result, we get an image with the edges enhanced and all other information like push a little bit down. And how it corresponds to the features, how it corresponds to the convolutions and filters that we are going to use in our neural network, that we actually, a lot of people use in image processing. So basically, in principle, they're pretty much the same. The difference is that at the beginning of our training, at the beginning of our problem, we do not know what weights we should actually put in those kernels. We don't know which features should be extracted. We may have some intuition, and probably in the past, many people tried, to manually craft some of the kernels, but it's not needed anymore. So the principle how those filters or those convolution work nowadays is that we initialize them with just random variables, just random numbers. It happens all along our neural network. And at the end of the day, we allow gradient descent and our optimization algorithms to train those weights. So not only we are training all the layers that are responsible, for example, for classification of images, but we are also training, we are also learning those filters. We are also learning these feature extractors. And the reason why we are using convolution is that is because we want to be, let me put it this way, spatially agnostic. So if we need to build a filter that detects a cat, we would like to have this filter in such a shape, in such a way that it works regardless in which part of the image the cat is. So we don't want to learn, we don't want to train a separate filter for the cat that is in top left corner and another filter or set of filters to detect that the cat or any other object is in the bottom right corner. And max pooling layers also help us, to account for some spatial to be spatial agnostic, and also helps us to make those features more abstract, more general. And on many occasions, when you do the visualization of those features, they seem to look pretty weird, but it is not, those features were not created for us. Those features were created for neural network. So the neural network were a little bit different than a human brain works, at least now. And what you see on the screen right now is an example of an architecture of image processing deep learning network. This architecture is called VGG16. It is no longer state of the art, but it serves its purpose. So this is to show you just how it works. So on the left-hand side, we have an image, it can be even grayscale, it can be RGB, it doesn't really matter. And then we have a set of layers interlaced. We have convolutional layers, so those with kernels that are meant to extract features, and then we have them interleaved with max pooling layers. And as you can see by watching the screen, by watching the presentation, I think you can tell that those that the deeper we go with this neural network, the image that we are processing is getting smaller, but actually the layer or the depth of next step is getting wider, it's getting deeper. And at the end, we have just a vector with 1,000 features that our intuition is that it will help us, it will allow us to do the task, do the job. And VGG16 was originally created for the ImageNet challenge. So the idea behind creating this architecture was to label pictures. So basically to detect to one of which of the 1,000 categories a particular image belongs. Is it cat, dog, a truck, this kind of stuff. And what is pretty cool and pretty amazing with those models, those architectures, they have been pre-trained for us. They are available on the internet for us to download. And the architecture was also put in a way, and the code exposed it in a way that we actually can use it without the last layer. So we don't really need to do the classification. We can take everything but the last layer and use it as an input to any other task that we may think of. So this constitutes one of the building blocks that we need to create our deep learning solution to translate mockups, to translate screenshots into HTML. So we have a way to represent what is on that picture, what is on the picture, that can be understood by other layers in neural network. The second element that we will need is a language model. So basically, the language modeling task is something, is a task to assign probabilities to certain words. And once we have a probability of a certain word, we can also extend this and think about what is the probability of a set of words, or a sequence of the words, or what is the most probable word that follows the given sentence, or follows the given sequence of previous words. And there are a lot of different applications for this approach. Just to give you a simple example, let's say that we have an algorithm that does a speech recognition for us. And we are unsure about one of the words. Let's say that is the last word in our sentence. We have two or more candidates. And of course, given this solution, the speech recognition, probably we have some probability associated with the last word, with the candidates for the last word. But what we can do else to help to get model with better accuracy and to have better results. Actually, we can train a language model, because now, once we have part of the speech translated already into a sequence of words, we can use our language model to predict which word is the most probable, or which of the words that the speech recognition software suggests has the highest probability. And if we combine those probabilities from language model with the probabilities given us by a speech recognition software, then in most of the cases, or at least I bet that it would make our solution more accurate. It also has a lot of different applications in other parts of natural language processing and, for example, image information retrieval. And we are also going to use it to generate HTML code. So for us, our language won't be Polish or English. We won't be trying to create poetry, which, by the way, is actually possible with language models, especially with GPT-3. If you have never heard about it, I highly recommend to Google for it, because this is an amazing piece of engineering. But now our language will be simply HTML, so HTML tags. We are going to generate HTML. And how will it work? So basically, we're trying to build a language model that, given a start token, will try to predict what is the most probable output. So for start, it will be HTML. For start plus HTML, it should be head. For start HTML and head, it should be title. So as you can see, we are going to accumulate our output over time and simply join it with the previous inputs. And this is the second building block that will be used to create the solution. And once we have it, combined with the image features, we will simply generate the HTML code recurrently. Now you may ask, how are we going to represent the text? There are a bunch of different ways of doing this, but let me show you one of the simplest one. Again, a refreshment. I'm just going to refresh your memory. We are not going to spend the next 20 minutes discussing different types of dealing with word representation, but this is one hot encoding. Our vocabulary are just those three words, this, is, and Sparta. So in one hot encoding approach, the dimensionality of the vector is basically the size of the vocabulary. This is why in this example, we have 3 columns. And basically what we do to encode it is we simply assign each of the words with a number. In this case, this would get a 1, is 2, and Sparta 3. And we initialize the entire vector to zeros, and we put a 1 on the corresponding indice in this vector. So this is why this has 100, is corresponds to 010, and Sparta is 001. Yeah, of course, depends on from which side of the are counting, but that doesn't really matter. We can if we were to use the indexes like in programming language, it would still be the same. Okay, so this was the first approach, and the second one that we will be using today are word embeddings. One-hot encoding is a nice approach, still used in some of the solutions, but it suffers greatly from the cause of the dimensionality, because we have this is Sparta, now then we have only 3 words, but if we imagine all the possible tags in HTML or all possible words in Polish language, then the dimensionality of the vector maybe thousands of elements or even hundred thousands of elements. So this is, and only on one place there is a non-zero entry. So having it as a dense vector will be a waste of memory. And still, we don't get any information about the meaning of the word whatsoever. And for this purpose, there was a famous paper, I believe it was in 2013 by Thomas Mikolov, where he proposed two architectures of neural networks to create something that's called word embeddings. So basically, it's a representation of the word as a numerical vector, but built in such a way that it should embed some information. Hopefully semantic and syntactic information about the word. And as it turns out, they happen to succeed because the word embeddings that came out from this solution, from those two architectures, were able to catch a lot of different aspects of the word and its surroundings, in its context. To that extent that even doing some mathematical operation on those words was possible. So imagine a situation that we have a vector that corresponds for Poland, another one corresponds for Warsaw. We subtract one from another, so Poland minus Warsaw, we get another vector, and that vector in this multidimensional space is just a direction. And if we look into that direction, if we take this, the result of subtraction, and we add it to Spain, and we search for the closest vector around, we'll get Madrid. So this particular direction embeds the concept of a capital city. And it turned out that there are many different directions that work in the same manner. For example, things that you can see on the slide are tense of the verb or just a gender, like if it's male or female. And actually, there's one of the most common examples from the word weg, that you simply take king, you subtract man, you add woman, and as a result, one of the closest vectors is queen. So this is the magic behind word embeddings. And we are going actually to use word embeddings for our HTML tags. Okay, so we have image features, we have covered a way of representing words. The next thing that we should tackle is how we are going to deal with sequences. Because image can be represented as a vector, it can be seen all at once. But when we are processing language, we are processing a natural language, or we are processing languages like HTML, it is sequential in nature. So we need to find out a way of dealing with sequences. And an architecture that we can use is called recurrent neural networks. The one that you see on the slide is called vanilla RNN. So this is the simplest solution, where basically we apply the same set of weights for all of the elements in our sequence. So basically this, to some extent, we can think about as an unrolling a loop. But this approach suffers greatly from some problems. So having said that, in RNNs, in vanilla RNNs, the weights are shared across all the steps of calculation. And if you recall how the gradient descent works, and we actually can see how the update formulas look like on the internet or maybe in some book, you will notice that because of those shared weights and because of how the cost function looks like, we are going to multiply the same matrix over and over again. And this causes a series of issues, which are called basically connected with vanishing gradients, exploding gradients, and some issues with training the networks. Why is it so? It's pretty simple. It's just because of the multiplication, because of the weights are shared. And imagine a number that is 0.9, and we multiply it by itself a couple dozen of times. So first it's 0.9, then it's 0.81, and so on and so forth. And at the end of the sequence that is like 100 elements long, it would be 0.9 to the power of 100. So you can imagine how small this number would be. And on the other end, we can have a number like 5. And at the end of the sequence, it would be 5 to the power of 100. So we may end up with either values that are extremely large or the values that are almost close to 0. And this causes pretty serious issues when we want to train such neural network, because if there is a 0 somewhere, then the gradient becomes 0, and if the gradient becomes 0, the update of the weights is also close to 0, which basically translates that there is no update, and if there is no update, this means that we learn nothing. And to combat those issues, there was another architecture proposed, which is called LSTMs. Let me just go briefly through the architecture of the LSTM, because this is something pretty crucial for us to understand if we are willing to work with the sequence models. So the core idea behind LSTMs is that it has a memory. LSTM stands for long short-term memory, because with RNNs the issue was that those networks were not able to remember the necessary information along the entire sequence. And this is what can we do about it. So in this case, we are creating something like a conveyor belt that's going to carry the information along the entire sequence. And at each step that we are getting some new information, we'll decide what to do with the current information, the current state of our memory. So this is something that is here called C subscript T minus 1 and C subscript T. And we are going to begin with the previous hidden state of our cell. We concatenate this information with the current input, so the new information that comes to us. We apply a sigmoid function to it, and this creates for us a forget gate. You may think about it like just a vector of numbers between 0 and 1, and it is up to the neural network to learn along the way which elements should be squeezed closer to 0 and therefore forget, and which elements should be pushed toward 1 or values closer to 1, so the LSTM cell will tend to remember these elements. So basically, the forget gates gives us a vector of numbers between 0 and 1. The next gate is called an input gate, which again calculates a vector squeezed by the sigmoid, which gives us numbers between 0 and 1. And again, the principle is the same. If something is closer to 0 and something gets multiplied by the value close to 0, it means that we won't be using it, that it's not necessary, that this update that comes from the current state, the current information and the previous hidden state is not that important. And if it's closer to 1, this means, okay, this is information we need, this is information we want to have. And having those two elements combined, we simply multiply the previous state of our memory by the forget gate, thus results in making, let me call it, some room for the new information, or just forgetting the things that are no longer relevant. And the input gate gives us what we want to add. And as you can see here, we are not multiplying CT times CT minus 1 anymore. There's no matrix multiplication like it would look like in vanilla RNNs. And the last step is we have to calculate what things we want to actually output. So again, we have a sigmoid that creates some kind of a filter for our output, and it outputs the information squeezed by the TOWN-H function, and also it creates the hidden state of our LSTM cell. So this is basically the LSTMs in a nutshell. So now we have all the building blocks that we need to create our POC solution. Because now we have a way of represent image, we have a way to extract image features, image information. We know how to encode text. We have a way of encoding information that comes from the text. And we also know what to do with a sequence of inputs. So, and all this information we are going to use to create our final solution. So this is, on the slide, you can see how, in general, the architecture will look like. And our first example, just a dummy one, a hello world example, will be built like this. We have our image, which will be just a hello world displayed on the website with minimal markup. Then we'll pass it through the VGG16 to extract some of the features. We have our tags, which will be just three of them. I will show you in a moment. Because we have that little tags, we can easily and safely use one-hot encoding for that purpose. We are going to concatenate the information from those two sources, feed it to the neural network, and get our prediction. Okay, so let me switch to a UPython notebook. Okay, I hope that it will run. Okay. Yeah, we are using TensorFlow. Here, I hope you can see our vocabulary. So this is basically the start token, the entire HTML code. This is the simplest way of dealing with it, and the end token that should tell our neural network that this is the end of our sequence. Yeah, so we basically can train this. This is how it looks like. Now we are going to pre-process the models. We are going to download the VGG16 model from the internet. This is how our first input will look like. So basically an empty token, and start token. And our expected output is this entire bunch of HTML tags. In this case, is this hello world. And the similar thing is for the second input. So our second input would be start token, HTML, empty token, start token, and HTML, and we expect an end token to appear. And here is the buildup of our neural network. Yep, here and here. We create our matrices, and we are going to train our model. And only now, the first epoch. As you can see, it already is able to create the first token right, but the second one is wrong. Here should be like a termination of our sequence. Let's add 20 more epochs for the training. Still not that much. And let's add some more. Oh, yes, and you can see this is a bit of overkill for this kind of a model. But anyway, at least we have proved that now this architecture is able to learn what we wanted to learn. I think we are running low on time, so I will try to speed up. So here we have our second example. This is an HTML example, a little bit more complex. This time we'll be using word embeddings for representing of HTML tags. Instead of VGG16, we'll be using a different pre-trained neural network, but it doesn't really matters. Then we are going to apply some transformation on both embeddings and the inception ResNet results. Will be like LSTM plus time distributed layers for embeddings and dense layers for inception. Then we are going to concatenate the features. This constitutes a step that is similar to encoder-decoder architecture. And then we will build our decoder from the LSTMs and dense layers to predict the next tag. And this should look like this. Let me close this one. All the code that you can see is also available with a blog post. Maybe it's not exactly the same code because I modified here a bunch of things, but I strongly encourage you to basically follow the original documentation, original papers, especially about pixel to code, and then try to work with this code for yourself. And here, as you can see, it generates the code recursively. So basically, we are feeding the previously outputted tags back to the neural network, and it generates HTML code for us. And you may ask how this code looks like once it finishes. And I have an example already copy-pasted for you. Okay, so if we go here, we go to HTML. So this is how this website would look like after only a few epochs of training. So it's not very promising. And this is how it looks like after, I think, 100 or 200 of epochs of training. So this is actually HTML code. It's not an image. And the original image is here. So as you can see, it looks like there is something in this neural network, in this architecture that can help us to create HTML code from the mockup. And the last most complex example is pretty similar to the previous ones. The only difference is that we switch some of the elements of our neural network. So this time we are not going to use a pre-trained neural network. This time we can use our own CNN, convolutional neural networks. Again, we are going to use embeddings and the previous set of tricks. And the rest of the architecture remains basically the same. Only in this case, it's based not on an HTML code, it's based on a data set from the pixel to code. This is for a markup, we are using a domain-specific language that will be compiled and to HTML and then present as HTML. And the images are the matrices saved in NPC format. But again, let me go here and hopefully it works. You never know during the presentation. Okay. Please forgive me that I'm not training all those networks live, but it would take a lot of time to train, and we won't definitely fit within this 45 minutes window. And we are basically out of time, but I hope in a minute we will get what we want, the two last cells, and we have index predicted and index original. So this is the original website design, and this is what we got. As you probably notice, it's not perfect. It is missing some of the elements, but at least it was able to get some of the elements. So I hope that I showed you today that there is a lot of things that can be done in this area, that this is pretty promising, and I strongly encourage you to investigate in this matter further. Thank you very much for having me with you today.
All right, thank you. Thank you for that very interesting presentation. Thank you for sharing that. We have time for one quick question. We actually have one viewer who asked here, what are some real life examples of usage of the whole algorithm?
To be honest, I haven't seen this algorithm live in any production grade code, in any production grade system. But there's a bunch of companies that heavily invest in actually invest time and money into researching this further. So please go to the Pixel to Code paper, and you will see. I cannot recall the name of the company now from the top of my head, but definitely a lot of, maybe not a lot, but a bunch of people is working on this, and not only on this per se, like a translation of the screenshot to code, but this is, as I mentioned before, it may be seen as a more general case, captioning of the pictures.
Mhm. Okay, okay. Thank you for that response. Unfortunately, we do not have more time, but it's never too late to ask more questions. So if anyone else has more questions, please do ask them on Discord, and Krzysztof will try to answer them later as soon as he can. But once again, thank you, Krzysztof, for this presentation.